I am Ty Roachford. I'm a PhD student at Florida Atlantic University out of the Machine Perception and Cognitive Robotics Lab there and associated with the Center of Future Mind also at FAU. And this is my talk, my first talk ever on my stuff that I'm working on for my thesis. Uh, Existence as the controlled variable, where I'll be talking about my framework, which I call Ensoul, which is about, in like perceptual control theory terms, I guess, studying and generating natural control systems. So I'm going to kind of go through this really quickly because I think the majority of you here are kind of really, you understand what a natural control system is. But yeah, there's been a bunch of different metaphorical lenses that people have used to view organisms. People thought maybe like a vital force or anima, something like this back in the day. Also, humors, the idea that fluids like bile, blood, and all these other things need to be kept into balance. And then we kind of moved on to like a mechanical clockwork version of how organisms are powered or driven, what's inside of them. And nowadays, we kind of think that, okay, it's not really about what they're made up of, but everything is surely like a computer in that it's computing a particular algorithm at a particular time. Maybe the function or the mechanism changes, but like it's still doing that domino effect like process from input to output. So I have this little domino chain here to illustrate that. The question is this an appropriate metaphor? Well, perceptual control theory, I guess you could call it like a child or extension of cybernetics, suggested not quite. Organisms are more like thermostats than they are like computers. So thermostats are not dedicated to producing their outputs like computers are. They're more like dedicated to producing their inputs. And so I have a picture here of this thermostat, and it's set at 72 degrees. And what it does is it's having some constant behavior where it's either having the fan on or off or the furnace on or off in order to achieve a temperature that comes in as input to be equal to this set point of 72 degrees. So it's got a sense temperature, and it wants to make sure it's equal to its reference signal or set point here. And organisms are very much the same. You have an organism that wants to be within a certain temperature value. So it's not a very particular temperature value, but it doesn't want to be too hot, too cold. Also, it doesn't want its belly to be too full or too empty. So it's also like a control system. It's not an artificial control system, but it does this same sort of thing, and you can model them in similar ways. And yeah. So again, just more motivation for why studying organisms as natural control systems. Well, it seems to be a better fit for the actual state of affairs we seem to find ourselves in. In other words, things just do seem to be more like control systems than like computers, given like the hunger thing, the temperature thing that we do know that organisms do. They're involved with a lot of homeostatic processes. They're keeping a lot of different chemical concentrations at like approximately the same level. But there's kind of another argument here, which is that like for anything that exists in general to be distinguishable from its environment, well, then that thing must be made up of a certain amount of stuff in a particular like geometry. So furthermore, for it to like stay as a thing that maintain its identity, it needs to maintain the amount of stuff that it's made up of, and it needs to maintain it in that particular geometry or a particular different sets of geometry, you could say, when it comes to more complex things. So I have a little image here of a super simple thing where it's consisting of two particles and it has this boundary. And by the way, can people see my cursor? Okay, great. And it has this boundary. And so basically for the only way that it can maintain its identity, so now this is a thing that exists. We go, oh, okay, well, we never see two particles that are super close to each other anywhere else. So this is a thing and it can be distinguished from its environment. And it's in this particular geometry. In the next clip, we see that another particle tries to kind of come in and hit it. And what it does is it ejects one particle and accepts the new particle so that it can stay and keep its identity. So this is just explaining that like there's this kind of ongoing behavior that it's doing, trying to maintain its particular mass and particular geometry. So I feel like it's an interesting logical argument for why like anything in general that exists can be looked at as a natural control system, anything that has evolved. Because for us to look at it and identify it as the same thing across time, it's got to be keeping up its same mass and its same geometry. And then quick little tidbit here again is that this is a very simple solution, a super simple thing, and they're often simpler, smaller in size, more adaptable than their analytical counterparts. And I'll show an example in the next slide of that real quick. So we'd expect like evolution again would discover and use more feedback control solutions. And Dr. Henry Yin has suggested that there is a crisis in neuroscience from not looking at the brain in this way. So, and this is, I think the big thing here is that it's like the behavior illusion, which you all are maybe familiar with, which is this idea that the true cause of the behavior is coming from the disturbance to the reference signal, which is inside the organism. And so what you see as the observable behavior is kind of more of potentially a side effect than it is an effect of the sensory input as it comes in. So I just have this little image here, and definitely check out Dr. Henry Yin's article, The Crisis in Neuroscience, to learn a whole lot more than that. He'll be eloquent with it, many pages. And so I have the outfielder problem here just as a demonstration for how we can model organisms as natural control systems. And the idea is like, how do organisms intercept objects? Like a ball is hit by a baseball bat, the outfielder has to go catch it. How does it do that? The first paradigm, the input-output computer metaphor paradigm, is where organisms have some sort of internal model in their head that embody Newton's equations. And then what they do is with their senses, they measure all the necessary variables they need, and they somehow plug it into that equation and then calculate the final position and move towards that final position. That's one way. But obviously you'd have to get the initial conditions perfect. Your measurements would need to be perfect to have a perfect calculation of the actual final position. And additionally, there can be noise. So maybe even if you are correct and like the wind changes somehow, then you're all of a sudden incorrect. And then maybe you think, oh, you could just solve this by like running the equation over and over again as you're catching the ball. And maybe, but it seems like it would lead to probably like a lot of bloat. I imagine that organisms would be much larger, whereas there's a simpler way of solving this problem, which is the control system approach. And what it says is they can simply take actions keeping the object that is flying in the air constant in their field of view. So the speed of the flying object. In other words, if the ball is right here and they're running after it, they want to make sure that the ball is not accelerating with respect to them, because then it'll land behind them, and they want to make sure it's not decreasing in speed, otherwise it'll land in front of them. So if they keep it just right there perfect, then eventually they'll get to the point where they catch the ball. And this is just like a simpler, faster, more efficient solution. It doesn't require you to know the end from the beginning. You're just adapting as the situation is changing in real time. Okay, so that's like the background. And the problem with all of this explicit modeling is that modeling is hard. It just isn't clear. Like, even if you're going for the computer things and you're asking, okay, what algorithms is this thing running? Or instead, maybe what variables is this thing controlling? Either way, it's really hard to come up with a model that actually replicates the behavior. And it's also difficult to understand what level of detail should be added to the model. And if you're not modeling at the most detailed level, then how do you model at a more abstract level and still get that same sort of behavior? The point is just our models are no doubt wrong. They're good. They're extremely helpful and they give us insight. But modeling in this way, where we're defining all these things, is difficult. Furthermore, once we come up with a model, even if it fits the behavior well, it doesn't provide insight as to the underlying mechanisms of that behavior. So, for example, okay, yes, now I know that maybe it seems to be keeping the flying object at a constant speed in its perceptual vision, but how actually does it even parse apart the fact that this is an object and things like that? How do we say what are the physical parts that are embodying this control system equation that I've come up with to fit the behavior? So I'm thinking that we need a science that allows us to go from these coarse-grained models of things that we make to multi-scale models of things that we make, where when we make a coarse-grained model, we actually can come up with an idea for how mechanics might be operating to support that coarse-grained model behavior. So scale-free complexity science through simulations is the idea. Suppose we had a simulated world in which we saw things that looked a lot like amoebas. They swam around, they ate small particles, produced waste, even had offspring. Then suppose that we reference our coarse grain model about how amoeba populations grow and shrink over time. It's something that we've, developed outside of this simulation. And we're like, maybe it's applicable to this. And then so we apply it to this and we find that, okay, this actually does seem to describe the population of these things that look like amoebas in our simulation. If this was a simulation in which we could zoom into the precise mechanical details of how the behavior was being produced, then we could use this simulation to understand the mechanical or physical instantiation of the amoeba, at least to some degree. It would give us insight as to, oh, okay, this is like a possible mechanism where all these parts work together to create this behavior that I am then modeling with my coarse grain equations or whatever. So data from simulations of this sort, I argue, could give us a better theoretical understanding of how to move from coarse grain models to even finer or more accurate models. Of course, the question is, how do we create such simulations? One might imagine that a simulation anywhere as near as complex as our world ought to have a pretty complicated setup, but surprisingly, it is not the case, and likely not the case. We found that it's very easy to get surprisingly complex behavior from very simple programs. So this is a cellular automata program, a very simple program that consists of just a grid of cells, and it's actually one-dimensional. So we can imagine that we start off with just this row of cells here. The cells are either black or white, and these rules up at the top tell each cell how it changes in the next row or next time step, if you will. So for example, we start off here with this first black colored cell and we go, okay, what rule corresponds to this? It has a white neighbor on the left, a white neighbor on the right. So we can check this rule and say, okay, if both of my neighbors are white, then and I'm black, then I stay black. We can also look at this one and see, okay, on the right, we have a black neighbor. On the left, we have a white neighbor. And so we're going to consult this rule and we see, okay, if I am white and my neighbor is black and my left neighbor is white, then we're going to turn black from white. And we just apply this to every single cell in the cellular automata to see what happens. And the expectation was, okay, it's extremely simple. We'll probably get some kind of extremely simple repetitive program, right? And apparently you don't. And it turns out to be really hard to predict what it is that you're going to get. It seems like we can get maybe arbitrary complexity. So this is on the side here. I believe this is about 20 steps, and this is steps after around 250 iterations. And we can see, we get some kind of interesting repeating pattern maybe here, but over here, something splits off. And then later, even more steps, you'll find that this same thing splits into two and then reemerges and does all sorts of kind of weird, complicated things that you wouldn't expect. And indeed, how complex can it get? Maybe arbitrarily complex. So this one actually, Rule 110, has found to been Turing complete, which means that it can run any possible computer program. So you could set this thing up to calculate 1+1, or if you're really ambitious, try to run Microsoft Word on it. There are a bunch of other cellular automaton rules that provide this Turing complete type behavior. And so the game of life, a two-dimensional cellular automata, is a really great example. Here is some of the rules that work for this game. And I just want to show a quick example that you can start off with this guy, and this guy is actually a known entity in the game of life, but I'll go ahead and just make some kind of random initial pattern here. And we get some unfolding of dynamics. This guy ends up remaining persistent, but the key point is nobody can be sure whether what I just did as an initial condition is going to end up going to be something boring or going to be something really interesting and incredibly complex. Indeed, what type of complexity can we get? Like I said, you can run any particular program on one of these cellular automata as well as the game of life. And so what someone did was actually take the time to go in and mechanically with their hands build a digital working clock in the cellular automata game of life. So it would be really cool if you got something like this, something really complex and interesting to pop up in a program without you actually hand doing it. The idea is that we would see something crazy and complex like this, and we'd want to zoom into the details and be like, okay, wow, apparently you can make something that tells time using this thing. How does it actually work? And then maybe how can we, apply how it works in this simulated world in real life? Take some of these principles, use it as a test bed to develop and understand the natural world. The problem with cellular automata and the like is it's not clear what rules will lead to complex behavior. We just have no idea what's going to happen. And even if we can figure out somehow that it's going to have complex behavior, then we don't know what the complex behavior will actually be like. Given that there are an infinite number of possibilities to explore, no principled way of finding the interesting ones, it's not really a practical route. And this is what I would call part of the problem of open-ended evolution, which I'll describe briefly in the next slide. This image here is just an image of what Stephen Wolfram calls the Ruliad. He's using simple programs, a collection of them to try to understand different theoretical principles of physics, kind of akin to what I'm suggesting be done here, but he's doing it definitely way more in like a physics, try to understand quantum mechanics and general relativity and how they're united and things like that. But this is just to show the incredible scope of what every possible computation could be like, and that searching through them, although you might find something crazy cool, is just not practical. So I say open-ended evolution through Eleatic games might be a thing. How can we, the problem of open-ended evolution is how can we create a program that results in the seemingly unbounded complexity growth that we seem to experience in our universe? Well, I don't yet have a particular program that does this. I think I have the right way for thinking about it. And this framework that I call Ensoul proposes a class of what I call Eleatic games, or games of existence, in which the only goal of the game is to persist one's existence. In other words, as perceptual control theory would say, existence itself is the controlled variable. All right. So Eleatic games. How exactly are we going to make an Eleatic game? Well, first we need to define what is existence. So Plato said way back in the day in a book called The Sophist that to exist is to be the cause of an effect. And I'm like, okay, that sounds good, makes sense. So then I say also, then for something not to just to exist, but to persist its existence, then to persist is to be the effect of some consistent causes, if that makes sense in this circular reasoning type way. You always have to have something that is causing you, and it might be that you are in some sense causing you a little bit. In other words, like, right, when you eat, you cause yourself to exist in this sense. So we're trying to capture this by putting it into a game, and we kind of, as a desirable, want to capture the physically relevant mechanics that are interesting, like keeping stuff local. Maybe like, okay, we know that energy is conserved in the universe, so maybe we make the amount of stuff in our universe conserved. As you saw in the Game of Life Cellular Automata, the squares can actually like disappear. Like we had a little glider guy running, but he can just disappear. It would be nice to make sure that all the stuff can't just disappear. It can become in different configurations, but can't just disappear. Okay, so we have a space that this stuff exists in, very inspired by the Game of Life. We have stuff, and the stuff is energy, let's call it, E equals mc squared. So apparently everything is just kind of like mass energy, some different form of that. And we have spatial partitions, and we need to have a mechanics of cause and effect. Like, so I say to exist is to be the cause and effect, to persist is to be the effect of some persistent causes. But what exactly does that mean? Well, we provide this little world here, and we basically say that the motion of energy must be local. And I'll show an example of that right now. So this is kind of how you play the Game of Life. I have a demo here, which I'm just going to kind of skip to and show real quick, or the Game of Existence. And so what you do is, to make everything local, is I say, all right, a cause and effect in this scenario would probably be the movement of energy, right? When something changes state. So when energy moves from one spatial partition to another spatial partition, we call that a cause and effect. If I was just to draw an arrow here, then only what we would see is just an effect. We would just see the energy moving, and we'd have nothing to point to say why it's moving. So we have to actually do another rule in the creation of our effect, and we say that it takes energy to move energy. So I'm going to say that this is the energy source. That's going to move energy from here to here. I'm going to click that. It's going to send a little energy particle there, and then it's going to just move energy from here to here. Now, eventually, if I add more so that the force is stronger and it's moving more energy from that spot, we're going to see that this will eventually become empty and this bar will disappear and the energy that was responsible for that movement dissipates. And so the idea is, all right, now I've just kind of lost the game of existence. I'm no longer causing an effect. So how can I continue to cause effects? Well, it would be probably something like if I go ahead and make a loop like this would certainly help to persist my existence. Now, depending on the rules of the game and how hard it is to move energy from one spatial partition to another, maybe this configuration works, maybe it doesn't. In any case, we're going to want a way to kind of like make it such that players don't cheat by just making a thing that persists forever and are like, yep, all right, I am winning. There is, in fact, no way to win the game of existence, but there is a way to increase your score. And so the way that I plan to do that is by using a combination of the information theory of individuality and assembly theory. So if I just go from here and skip over to here, this is all the possible ways that you can make moves within this little space that I showed you. And this is just the starting space. And this is just the starting space. And we can imagine that there could be a thing right here and there could be another thing right here, and maybe they're interacting. Or let's say in general that all of these squares are, they should be considered individuals. We shouldn't consider the whole thing as an individual. The question is, if things interact, and they must interact by touching, like we're by causing an effect onto each other, like they have to be in some kind of causal relationship, then how do we actually parse out different things? We take this for granted right now in our science, where, you know, we look at all these different things and we assume this is the best way to kind of be looking at things and approaching things and taking actions. But it may not be the case. So I'm looking into the information theory of individuality, which says that basically a thing is a thing if it's persisting itself through time, and it depends on the amount of mutual information that is being shared between these things. And it's just a very interesting, cool thing I don't have time to get into full depth in right now, but it will allow you to identify individuals within your crazy causal network graph that you created to help yourself exist. Not only that, we can then use this thing called assembly theory to essentially quantify the complexity of those things. And so if we know how many things we have and how complex those things are, now we have metrics to actually drive complexity. And of course, the more stuff that appears that you create, the harder the game is going to get. And so the game is only as difficult as the player is skilled. And the way that a player can get really good at playing this game is probably by looking at something like our loop here that we have on the right and being like, okay, this is starting to bog me down. I don't want to look at each one of their stress levels individually. What I want is some kind of coarse-grained representation of this, such that I can take also more coarse-grained actions that tell me how to go further without doing such work at the micro-detailed level. Yeah. So you can imagine creating these cause and effects one by one, but you can also imagine creating them in arbitrary kind of spatio-temporal sequences, right? And you'd want ways for you to be able to look at the situation and say if what you're doing is good or not. For example, you want to make a bunch of causal powers on the left, and you want to know, is that going to be good for this thing that you just created? And hopefully the coarse grain representation will give you an idea of that. All right. So last thing that here I want to point out is that this is an infinite grid. It expands as you do things, and you can also move the energy that moves the energy. So you can make things that will essentially, we could create some internal network even smaller, which you can see here, that this is all the possible ways you can move energy from each spatial partition. But this one to the right, involves all of the ways that you could move the energy that's moving the energy, which would allow you to create a thing that actually moves across the field by itself. And so if you were here and you made one of those things, it would move across the field by itself, and you could actually see that because it would increase your visual scope. So your visual scope also has to do with how good you're doing. You won't be able to see everything, and you don't know what's going on outside of your actual vision. And finally, I just want to add some metaphysical spookiness because it's Friday the 13th, so I can't let you go without that. Real quick, there is an idea called the interface theory of perception by Donald Hoffman. He ran an experiment to figure out whether organisms embedded in their environment would be able to pick up on traces of the true nature of reality using only their senses. His results showed that the probability of this, like, in other words, do I see the same red that you see? And are they like really the same red? Do they reflect redness that's really out there in the universe? Apparently, his results show that the probability is 0. So a good analogy of the consequences of that is that you can imagine two people playing a game together. One person thinks they're playing Grand Theft Auto. The other person thinks they're playing Fortnite. One might say that each organism in general thinks that it's playing a particular game, and that those who think they're playing the same game or similar games define a species. So when we're building these Eliadic games, the rules are the laws of physics, and the actions of the players are what determines what actually happens inside of the games. Players of the Eliadic games must build their own coarse-grained models in which to see the world better and more quickly know what actions to take, and this in turn dictates how they see the world and what they will become. So what might we find out about our relationship to the nature of reality from such approaches? Thank you. Yeah. From the MPCR Lab, Center for Future Mind, Florida Atlantic University, I'm currently working on automating gameplay of these games so that I can have autonomous simulations. Humans can play the 2D one, but they probably won't be able to play the 3D version or versions with way more complex non-local rules. I want to work on applying, again, the like different theories of individuality. The information theory of individuality is just one, and then assembly theory, developing like that as an abstract measure for this game and also different types of Eliadic games. And then I'm rewriting my original paper that got me invited to the talk called Ensoul to highlight this Eliadic game concept, but I talk a lot more about a bunch of details in here, I think, and that's it. Thank you so much.
Super good. Are there questions for Ty? I saw Bruce, you shared something in the chat, but it was a direct message you have to share to everyone. And there's a question from Joseph.
Yes, that's Bill's paper on the origins of.
Oh, you should paste it again.
Paste it again?
Yeah. I'll chat with you. Joseph, you have a question. Yeah.
No, that's all.
Yeah, great talk, Ty. That was really interesting. I love how you're hitting all of the biggest questions possible. In the complexity theory approach that you're taking, you're kind of basing a lot on cellular automata and Wolfram's work, and that seems to be grounded in a kind of discrete fabric of space-time and energy flow. It's often the case that a lot of the most powerful control systems are analog and continuous valued. So how do you see that reconciling like this discrete operations in the computation versus like very strong control as far as the emergent autonomy and personal identity? Be interested to hear that. Thanks.
Yeah, I think it's okay, I guess, for the same reason that Wolfram maybe thinks it's okay. Well, he thinks that maybe the bottom could simply be discrete. I think it's a bit of a practical thing. We don't have a good way to represent like actually infinite real numbers, and we can always approximate these infinite real numbers with enough discrete stuff. So I'm like more of a practical thing rather than an ontological thing where I'm like, okay, well, I just need enough of it, like numerical methods used to calculate integrals or something like this, continuous things. If you have enough of it, you can approximate the continuous. So, yeah.
As long as the universe is computing those integrals, then you're good.
Yeah,
Cool.
Are there other questions for Ty? Well, thank you so much for sharing your work and taking us along in these games and these thoughts. We expect much in the years to come from this development.
Cool. I'm very excited. Thank you so much. It's super
Thank
perceptual control theory inspired, so I'm glad that you all like it.
Yes. Thank you.
Thanks.